begin. Thanks for coming out to the residency, and I just want to give you a little bit of background about me as the speaker. I'm coming to you from Los Angeles. I work at the LA campus of the Chicago School as a methodology expert for the National Center for Academic and Dissertation Excellence, or NCAID. Dr. Gillette is one of my coworkers, and we basically help students en route to writing their dissertations. Now, from my end, I focus, as my title implies, methodology. So what I want to talk to you about today is quantifying intervention effectiveness in single case research designs. So that's a bit of a mouthful, but basically what it boils down to is taking what is typically done, which is visual analysis of results, and putting some numbers to it. So saying, what percent of an improvement was there, what type of change has happened in the rate of a behavior based on an intervention. So in a nutshell, that's what it's all about. And what I want to do first is kind of give you a brief outline of the presentation. The first part of which is, again, visual analysis of results and kind of how this is the historical standard in applied behavior analysis. And then we'll look at how effect sizes have been developed for ABA. I'm going to give a few examples. There have been a ton of them that have been developed, but what I want to focus on is this specific one called non-overlap of all pairs, or NAP. And this is because it's basically, it has a lot of advantages, very few shortcomings, and it's also easy to calculate. So all that being said, I've kind of sifted through the literature and looked at what's out there, and this is what seems to be basically the standard that's developing over the last, 10 years or so. Then once we get through that, I want to have you all do an exercise using the NAP to kind of get your hands dirty with it a little bit, get familiar with it. And now my understanding is that, Aubrey, you printed out that sheet that I emailed to you. Is that going around to everyone?
Yes, it's right there.
Okay, perfect. So we'll get to that part. Don't worry about that just yet. Just hang on to it. It doesn't matter if it doesn't make sense for now. We'll get through it. And then finally, I want to look at how NAP is applied in different types of ABA studies. So, we've got reversal designs, right, where you have like AB phases, for example, and then multiple baseline designs where you're applying different interventions to different behaviors and then waiting to do another behavior and perhaps other different types of settings and across individuals, right? So we'll look at all of that. And then finally, the last piece that I want to look at, if we have time, is parametric effect sizes. And these are essentially where you can calculate the standardized mean difference between two conditions. And, I mentioned that the NAP technique has a few shortcomings. These parametric effect sizes are a kind of peanut butter to the jelly, if it's deemed appropriate. And I'll look into what that means when we get there. But for the time being, just know that these parametric effect sizes are not always suitable for single case research. So that's why I kind of have it as an appendix. It's like, okay, if you have the opportunity to use it, great. If not, then you don't really need to worry about it too much. And we'll get into all that. Okay, so to begin, here's just a basic example of an intervention and its results. So here we have two phases, right? One is baseline, and then this vertical line represents the point at which you introduce an intervention, and then everything after that is called the treatment phase. So you can see that the y-axis shows the number of out-of-seat behaviors. It's kind of taken from this study where these authors, Pierce and Cheney, summarized a bunch of stuff, and they talk about this one example where the child in question was getting out of their seat at inappropriate times of the day. So, it's a school environment, and the problem behavior that they're trying to address is the child getting out of their seat. So as you can see, there's, a pretty steady baseline rate at which this happens. The intervention is then introduced, and then you can see that that it decreases, right, with this one exception up here. And that's great. You can look at this and see that the intervention seems to be effective, right? And that's really great. Now, another example of the same kind of study is this. Now the baseline is really much more variable, right? So we can see that it's low on day 1 and 2, but then it goes really high on day 3, really low on day 4, and then really high again on day 5. Okay, so now if we look at this kind of data, the picture's a little different, right? You could still say that on average during treatment phase, the out-of-seat behavior is lower than in the baseline phase. But if all you're able to say is that it's improving, it's not very precise, right? We can certainly see that there's an effect, but what can we really generalize from it? What can we say in addition to just saying, hey, look at the data, you can see that it's effective, right? Not very precise language. So that's where the shortcomings of visual analysis really come into play. The first of which is that it's subjective and unreliable. So if you're a behavior analyst and you're in a school setting and you're saying to your stakeholders, okay, look, we can see from the graph that it's effective. Well, okay, that's great, but what does that really tell us other than what we saw on the graph? Not super strong. You want to be able to say that it's more than just sort of effective, or you kind of say, how effective is it? Well, look at the graph. Okay, fine. We can do a little bit better. A corollary to this is that when you look at, or actually before I even skip ahead to that, another piece about the lack of objectivity here. If you think about alternative interventions, right? So if you have two graphs of two different interventions and they look kind of similar, well, which one should you choose, right? If they both look similar, but maybe one is a little bit better, wouldn't you want to go for that one? So that's another shortcoming, is if you can quantify that and put a number to it, then you can clearly go with the choice that is even slightly more effective. And even if they look the same, quantitatively speaking, one might be better, but just by looking at it, you might not be able to tell. Moving on to this next point about visual analysis, it's useful only in the immediate context of that particular student in that particular classroom, and you can't really compare the effectiveness of the intervention to other similar studies. So if you go in the literature, you can see, okay, look, this type of intervention has been applied in, let's say, 10 different case studies, single case research designs, right, that have been published. And if all that you have is visual displays, these kinds of graphs that we saw on the previous slide, then you can't directly compare the effectiveness of the intervention across all those different students. So if you're trying to get an idea of how effective this intervention is and whether you should or shouldn't use it, or whether you want to figure out how your client is doing compared to other clients who have had the same type of intervention, you can't really do that just by looking at the graphs. It would be much easier and much more scientifically valid to be able to compare the numbers directly. And so a follow-up point to this is that you can't conduct what are called meta-analyses. And this is a very important point, because when you try to look at the global efficacy of an intervention, it's very useful to the scientific community to, at conferences or for putting together like a sort of review of an intervention, to have a quantity that on average applies to all students, right? So the more people do this kind of study and the more people quantify the effectiveness of the intervention, the better we can all communicate and put together an overall measure of an intervention's effectiveness, which is what meta-analysis is all about. And basically what it means is you take a bunch of studies that are single case research studies and basically establish on average how effective they are, without just saying, look, here's 10 different graphs and you make sense of it, right? We can put numbers to it and get an average effectiveness. And certainly if you look in, once you start writing your dissertation and everything like that, and you start doing literature reviews, meta-analyses are very powerful types of studies where you basically get an idea of how effective an intervention is, because they summarize a ton of different, well, a ton, I mean, it depends how many there are, but they will summarize a number of the same types of intervention and say, okay, look, this is how effective this one is. You can look at another meta-analysis of a similar intervention, see how effective it is, and directly be able to compare them. And without quantifying the effectiveness of an intervention, you can't do that. Okay, so another very important point. Visual analyses increasingly do not meet evidence-based grant requirements. What this means is that if you're trying to develop a program, for example, or if you're trying to evaluate a program, or if you're trying to get funds for establishing any kind of center or research study, more and more and more over time, like I said, since about maybe 10 or 15 years ago, the government, I don't know if anybody's ever heard of IES, but it's sort of the government agency that is responsible for granting funds for ABA type of studies. They are more and more requiring that you have these kinds of numbers to establish how effective intervention really was with a particular student or with a group of students, or in a school, or if you're doing a kind of analysis of what we're going to be doing, then you need to indicate, okay, look, this is the efficacy of this type of study, and this is what I expect to find in the clients that I'm serving. So if you don't have that information, then you're less likely to get that grant, and it's just important to have this in the back of your mind, because in the future, as a practitioner, you're probably going to run into the situation sooner or later where you're going to try to get money to conduct your studies, and you won't be able to do so unless you have this sort of ability to quantify effects in your toolkit. Okay, so with that, I should probably note that historically there is a little bit of quantification in some studies. Like if you go back to the 70s and 80s, some people did indicate on average what the effectiveness of an intervention is, but it's a really small percentage. So as you look at more and more recent studies, you're going to see more and more of this type of analysis where they quantify different effects. And in fact, even if you look at the older studies and they say, okay, on average in the baseline, it's this much, on average in the intervention phase is this much, that's typically what they would do, is like report a mean or something like that. But if you look at this example previously here, okay, so look at the average in this baseline, right? It's like maybe like 11 or so, right? Just hovering right above 10. Here, let me draw that in here. It's hovering right about here, right? And then you can see that in the treatment phase, maybe we're like here on average. That's supposed to be a straight line. I'm using a trackpad, so it's tough, but you can see that no, we don't like that. What I'm trying to do is say that the change is from, trying to draw an arrow from up here to about down here. So you're seeing an improvement of about 5, right? Okay. In this example down here, in the bottom example, whoopsie. Hang on. Go back. Oh, I don't know how to erase these things. I feel, there it is. Okay, here. Okay, boom. Forgive me. Okay, I have to click on the little pen icon again. Here we go. Okay, so right, so we know that it's like this, but notice here in this example, it's all over the place, right? Like the baseline is all over the place, but still on average, it's still right about 11. So the idea is that if all you're doing is saying, okay, here's the average in the baseline and here's the average in the treatment, that isn't super informative, right? Because the variability of the baseline is going to be a very big indicator of what's going on before you even do anything. So this is just one example. It was actually designed this way by Pearson Cheney to actually illustrate this fact. But as we'll see, the way that we want to quantify these effects has sort of evolved over time. So in the 70s and 80s, like I said, it started looking at the average before and the average after. That's not enough. So what they've come up with are some metrics that are more precise and more descriptive and more appropriate to the kind of data that we deal with in ABA. So the question with quantifying effect sizes is how large of a change is there across two conditions of interest, right? That's what we want to know. In that example that I just showed, it's looking at baseline to treatment. And that's kind of the example that will follow through all the way, but then I'll show you how you can apply it, not just to two phases that are back to back. You can do really any two conditions of interest. And that's why it's important to note that it's, oh, I don't want that anymore. I want the highlighter. What we want to know is, what we want to know is how much of a change there is for any two relevant conditions. And when I say relevant conditions, that can mean anything. But again, we're going to be looking at examples where it's just like, baseline, intervention, and then go into more specific examples. So these effect size quantifications are going to apply to both reversal and multiple baseline designs. I believe that you guys looked at both of those earlier today. Is that true? If you could nod for me or shake your head. Yes? Yeah. Okay, cool. Then I don't have to go into that. But yeah, it applies to both of those. So we'll look at examples. And it also applies specifically to comparing two sets of data points. For any one of these effect sizes, regardless of what type of phase you're comparing, it's always two that you're comparing at a time. So for example, again, baseline and post-intervention, right? Or, once you start implementing the intervention and you start to see the trend go up, you can call it an intervention phase. Sometimes you look at the baseline phase, apply the intervention, and then you have a third phase where you just look at how quickly it the behavior either extinguishes or reverts back to baseline. Anyway, doesn't matter what the two phases are, you're always comparing two. All right, that's the take home. And then after this, let's just look at some actual examples of the different types of quantifications that have been developed over time. And I'll show you some pros and cons of each, especially as we go sort of in a historical fashion. We're going to go chronological order, essentially. So the first one that was essentially developed as an alternative to just saying, what's the mean before, what's the mean after, is percent of non-overlapping data. And what that means is you take the maximum point in the baseline. So here we have, this is the baseline phase here, where it says the number of observations is 10, and you see that it hovers about 4, 3, 4, and then there's this highest point of 7, right? And then it goes back to like 5, 3, 2, 3, 2, etc. And then what you do in this type of analysis is you look at that maximum point, and then you look at and again, this vertical line represents where the intervention starts. And then you're looking at every data point that's higher than this maximum point in the baseline. And all of those that are higher, you count them up and then divide by the total number, right? And that gives you the percentage. So if you have 1, 2, 3, 4, 5, 6, 7 out of 11 that are above, 7 by 11, oh gosh, I don't have my calculator handy, but it's about 70%, right? And that would be the quantification of the effectiveness. The trouble with this is that if you have, well, there are several points I want to mention, but the first point is that if you have this really outlying data point in the baseline, it's not representative of all the others, right? All the others are hovering around 4 or 3, and then this one is like 7. Okay, well, was that child or was that client having a bad day? Was there an error in measurement? What kind of issues could have led to this really outlying point? And regardless of what it may have been, you have this one data point that's just a huge outlier, but it's the one that dictates how you measure effectiveness, right? So that's a problem. Another issue is that all large effects look the same. So let's say that you have the baseline looking like this, right? Every data point in the intervention phase is above that outlying value, right? So you see that it would be 100% effective, basically. Now, what happens if you have the data looking like this, right? Clearly, that's more effective. But they're still all above that highest point, So it's still, you're kind of hitting the ceiling effect where no matter how much improvement there is, once you're at 100%, you don't have any sensitivity to detect anything above that. Now, this is a criticism of all of the effects that I'm going to show you, and this is where those parametric tests that come in the appendix at the end of the presentation are going to come into play. They allow you to estimate the magnitude of that large effect, and that's why I want to look at those at the end. But at the same time, they have their own shortcomings. And in reality, you know, if you ever have an intervention that's this massively effective, you know, you deserve a medal, right? So it's not really that big of an issue because most of the time you're not going to have such a huge effect, right? But you should be aware that all of these quantifications have this technical shortcoming, all right? Now, moving on from there, there's another issue. The issue being, again, related to that idea of the baseline. So looking at this, you know, I just kind of cheated and scrunched up these data to show what might be happening. So let's say that this is your highest point, and this is a more realistic example, right, where you might have a little bit of improvement. You have these 3 data points above that maximum point, and the rest are below. So this is just an illustration of that previous point, where if you have that maximum outlier as your criterion, that is a big outlier, and all the progress that's made is ignored. Because you can clearly see that if we use this point, the second highest point, gosh, that was like a huge improvement, right? So that's the really big problem with percent of non-overlapping data. And so one issue that was identified is just this. So one of the ways to summarize all this is kind of here on this slide, where, you know, all large effects are the same. Any variability can be due to outlying observations in baseline. So if you have one client who has an outlying observation, it's going to look like it's not effective. If another client doesn't have that kind of outlier, it's going to look much more effective. So it's not necessarily that the intervention is effective, it's that the baseline by which you measure it is variable, right? That's why we've got this point about variability here. And again, due to these problems, it's difficult to distinguish between published studies. So this impedes scientific progress because, again, we can't communicate about how effective intervention is. And in fact, the client may suffer. So if you look at a client who, for example, didn't have, you know, a client that had this type of maximum baseline, they might look like, oh, wow, you know, we should really use this intervention because look how effective it is. But then you look at your client using the same metric of percent of non-overlapping data, and they do have an outlying data point, and all of a sudden, you know, it looks like it's not very effective. And so you say, oh gosh, you know, I failed. But, you know, that's only part of the story because this is just one measure, right? So one thing that was done to alleviate this was to no longer use that maximum point, but to use the median. Can you get a show of hands? How many people know what a median is? Okay, a few people. Okay, the median is just the middle value. If you ordered your observations from lowest to highest, it would be the one right in the middle. So here we have, you know, a 4, a 3, a 4, a 3, a 4. So you have 2 3s, 3 4s. Actually, I'm sorry, we have 3 3s, right? 3 3s. Let's start with the 2s. 2 2s, 3 3s, 3 4s, a 5, and a 7. So in the middle of those 10 observations is, you know, you're somewhere between 3 and 4. And so you basically assume that it's 3.5. Well, you don't assume. You can basically find it because there's no middle value. If you had an odd number of observations, you have one that's in the middle. If you have an even number of observations, you have to take the middle two and take their average. That's why it's 3.5. And so this percent exceeding median measure was an improvement as an alternative to the percentage of non-overlapping data. And essentially what this does is it says, okay, well, again, what percentage exceeds that value? Now, this is a bit of an improvement, But again, it faces the same problem where medium to large effects are all quote unquote the same, right? No matter how high or how low that intervention phase is, as long as most of it is above the median, it all looks like 100% effectiveness, right? Because all those data points are going to be above the median. And the same issues apply, where because of this issue of all these effects looking the same, it's difficult to distinguish between published studies, and in turn difficult to interpret whether or not the intervention is effective or not. Okay, the advantage of it is, of course, is that it's resistant to that outlying value that was used in that previous type of intervention. So, these are two examples of these kinds of quantifications, and there are a ton more, but they all have these kinds of like nuances of, okay, let's use the mean, let's use the median, let's do this, let's do that. They all have similar kinds of shortcomings. So the one that I want to skip all the rest. I want to focus in on one that is a kind of a total shift away from this kind of analysis, and it's called non-overlap of all pairs. Now, at first blush, it's like, whoa, what is going on here, right? Look at all these arrows, look at all this stuff. Basically, what we're looking at here, to kind of just break it down, is what this illustration does is it shows one data point. And again, look, we're looking at this maximum outlying data point here, right? All the arrows originate here. What this technique does is for each baseline data point, it compares it to all of the intervention data points. So you would do the same thing for data point 1, data point 2, 3, 4, all of them, and compare each of them to each of the intervention data points. So what you're looking for, and so this is just one point, right? So you're basically doing this 10 times. And that's what that's what the handout is all about. So if you look at, well, we'll look at it later, but basically you can start paying it, put that in the back of your mind where we're going to be sort of counting the number of overlaps for each baseline data point compared to each intervention data point going across. So here, what we're doing is we're saying, okay, so for every data point in the intervention phase that exceeds this one, we call that a non-overlap, right? So you see that all the arrows going up are labeled N, right? Because they're non-overlap. And keep in mind, in this example, we're looking for non-overlap in the sense that we're looking for increases in a behavior. A lot of the time what you're looking for is decreases in behavior, in which case, non-overlap would be ones that are lower. Does that make sense?
Yes.
Okay. So here, anything that's above this value of 7 is a non-overlap. And for each non-overlap, you add 1. So essentially, what we have is we have these 1, 2, 3, 4, 5, 6, 7 non-overlaps. We have 2 ties, right? Because this data point and this data point are 7, which is where you would count 0.5. And then here are 2 that are lower, so these are overlaps, all right? And what you do is you basically count them up, right? You see that it's 1 plus 0.5 plus 0.5 plus 1. And that's one way to do it. Another way to do it is count 1 for each non-overlap. It really doesn't matter which way you do it because it's all just a zero-sum game. But in this example, you can see that it's adding 1 for each overlap and 0.5 for each tie and 0 for all non-overlap. So, you could have 7 zeros added here, but it doesn't really mean anything. It doesn't add anything, so it's not counted. Meanwhile, these data points is the same thing. Yes?
Can you repeat that?
You don't add anything for the non-overlaps. So you could add 7 zeros right here, but you'd just be adding 0. So there's no point in writing it out, essentially. Is that what you're asking?
And for the... Can you repeat the entire counting again?
Sure, yeah, of course. So basically, this data point is a 7, right? And so what you do is, for data points in this example that are lower, you count them as overlaps. So here you have 2 overlapping data points, right? Because they're lower than that data point. These 2 data points here, let me actually circle them. That'll be a little bit easier because it will allow us to refer to the same thing. Okay, so these two data points, right? For this data point, they're overlapping, right? Because they're below it. But for this data point, they're not. You see that, right? Because they're above it. Make sense so far? Okay, so what we're doing though is we're only looking at this data point here for now. We do them one at a time essentially. And so these two overlaps, each of them gets a 1. That's what this represents, and that's what this represents. Okay? And then these two here, this t and this t, these are ties because they're both the same value as this one. So they're counted as 0.5 because they're neither overlapping or not overlapping. They're the same. So that's why they're 0.5. So far, so good? And then I'm going to assume that's a yes. If not, just speak up. And then the rest of these guys here, these are all non-overlapping because they're above that value of 7. So they would be counted as 0. So you could certainly say, okay, 0 plus 0, dot, 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 there's 7 of them, right? But, 0 plus 0 plus 0, it's all 0. So it's just shorthand to not include it in this little calculation here. So let me just erase all that. And then what you would do is you would repeat the process for every data point in the baseline. So you see that for this first one, they're all non-overlapping because they're all above it. So that's why it's 0 out of 11. All of these are 0 out of 11, except for this one here, which has 2 ties, right? Because this one and this one are, they're both 5, right? So they each get 1/2 as the count. Okay, so that's this technique. Now, what it all does in the end. So here's just a sort of an overview of what I just said. It's the number of comparison pairs showing no overlap divided by total number of comparisons. Now this is a little bit counterintuitive because, again, it depends on whether you're going up or down, right? So if you're looking for a decrease, non-overlap means something different than if you're looking for an increase in the behavior, like we said. In other words, it's the percent of non-overlapping data between baseline and treatment phases. Essentially, you're taking each data point in the baseline and saying how much overlap there is in the intervention, and then taking the total for all the baseline data points compared to all the intervention data points. And there is a major, like I said, this is a sort of alternative to all those other ones. Was there a question? Sorry. No? Okay. It's a comprehensive test of all possible sources of data overlap, all baseline versus all treatment data point comparisons. Now that's just one example. Remember I mentioned at the beginning that you could have this, you could compare any two phases that you want. If you have a reversal design like an AB-AB, you could take the first baseline, compare it to the second intervention phase, or the first intervention to the second intervention. If you're interested in all kinds of different research questions, it doesn't matter which two phases you're comparing. The method is the same. And the other advantage is in interpretability, because a value of 1 indicates perfect improvement, a value of 0.5 indicates no change. In fact, it indicates 50-50, right? Literally, it's 50%, which means that half of the intervention data points are above and half are below, on average, each baseline data point. So that's a very meaningful number, right? And then 0 indicates perfect reduction. So that would mean that all of the intervention data points are, below all of the baseline data points. So it's a very elegant technique. Okay, right. So yeah, 0.5, very important. and it again indicates 50-50 odds that any data point phase B is higher than any data point phase A. So if you're above 0.5, you're doing better than no change. If you're below 0.5, you're doing worse than no change. And so that helps in terms of interpretability, right? Because now you can actually look at the graph and put, a sort of quantity to it and very quickly understand what's going on. Okay, now calculating NAP. This is where that sheet that you got comes into play, right? You all should have this in front of you. So what we have is the values that are going down here are the baseline data points, right? So we know that it's 4, 3, 4, 3, 4, 7. That's that big outlier that we've where's my mouse? That's that big outlier that we saw before. And then going across, come on, where'd it go? Going across is where these are all the intervention data points. So what we're going to do on that sheet is just follow steps 1, 2, and 3. For each phase A data point, add 1 for each phase B data point that exceeds it, add 0.5 for each phase B data point that ties, and add 0 for each phase B data point that is less than that phase A data point. So let's do the first one together, right? So we're looking at the first, here, let me erase this. We're going to look at the first row, meaning we're going to do the first baseline data point. So for 4, 5 exceeds it, right? So we add a 1. 9 exceeds it, that's a 1. 7 exceeds it. In fact, you can just kind of scan it and see that they all exceed it, right? So here the total is 11. And then all that we do in this technique is do the same thing for each of the baseline data points. So next, go ahead, take a few minutes and do the rest. And then when you're done, I guess Dana, can you let me know when everybody's done?
Yes.
Okay, thank you.
Can we go on the screen to see what is 0 and what is 0.5?
Can we go back to the last slide?
Oh yes, of course, right. Yeah, I'll leave this up so that you can see what happens. So yeah, so you add up all the values. When you're done, you add up all the values here. So this total column, you're going to get a bunch of different numbers in all these cells, going all the way down here. And then here is where you just add them all up. And then the last step is that you divide that total by the total number of comparisons. And we know the total number of comparisons because there's 10 phase A data points and times 11 phase B data points. So 10 times 11 is 110. So that's, if all 110 comparisons are, non-overlap, then you're back at 1 and so on and so forth. So with that, go ahead. If there are questions, raise your hand. If I was there in person, I'd be walking around seeing how you're doing. But basically, if there are questions, just let me know. Oh, and you can work in groups too. I don't care if you work in groups.
One more time. Does everyone have an initial amount?
Three.
It looks like most people have an initial count.
Okay. All right. Well, then here, compare yours to this. Is that about what people got?
Yes. Yes. We got some yeses.
Yeah. Okay, so this, I mean, for a first try, if you're off on a couple of them, that's perfectly fine. I made a couple of mistakes when I was doing this the first time, but I mean, it becomes, with practice, you very quickly get really good at this. Now, obviously, this example is very straightforward, that it's an effective intervention, but with real life, you're going to have a lot more 0.5s and zeros in here than this. But essentially, this is a very elegant way to say how effective the intervention is. Now, it's 96% of intervention data do not overlap with baseline data, right? If you're looking at a visual representation of this, you can't really say that. You can only say, well, look at the graph, it's effective, right? But now we have a standardized way to basically say, look, this is the effectiveness. Other researchers who are familiar with this now know, okay, I understand what that number means. And we can not only help clients by comparing how effective this intervention is for different clients, but also build the scientific literature base by publishing this information, by sharing it at conferences, by doing all kinds of sort of synergistic professional development and saying, look, I know how effective my intervention is. This is the number I'm using. And it's like a common language that you can now share with other behavior analysts. So, okay, that being said, I kept kind of alluding to this idea, what are we talking about? We can use different kinds of phases and compare them to each other. There are multiple definitions that you could use. So first of all, in a reversal design, right, you can have multiple reversals. I have A, B, A, B, so I'm just labeling them A1, B1, A2, B2 in order of time, right? That's what those arrows represent. So you can compare A1 to B1, or A2 to B2, or B1 to B2. It really depends on what comparisons are logically relevant in terms of your hypothesis. When you're putting your dissertation together, keep in mind that you can make these kinds of comparisons in different ways. So I was working with a student a couple of months ago, and he wanted to look at, oh gosh, the term eludes me right now, but basically how well the intervention sticks even after you remove it over time, right? So he says, okay, I want to compare how B1 looks compared to B2 after you remove it in between, right? So he had a couple of different students where the time, the A2 period was longer for one student than the other. And he said, okay, well, how does that affect the change from B1 to B2? And so you can do that. The worksheet doesn't care what numbers you put in there, right? It's all about the theory that you bring to it and what you're hypothesizing is going to happen. And then again, this point below here, the change in which direction, we talked about this where sometimes non-overlap in one direction indicates improvement. Other times it means reduction. So again, if the goal is to increase the rate of behavior, higher scores in phase B indicate non-overlap. But if the goal is to decrease the rate of a behavior, lower scores indicate non-overlap. That's why it says vice versa. Oh, I'm sorry, that 0 should be a closed paren. Sorry about that. But anyway, the bottom line is that you can compare two sets of data points and make your conclusions. Okay, so we saw a reversal design. Yes, go ahead.
Where did the 110%, where did we get the 110?
Can you repeat that? I didn't hear that.
Total opportunities.
Where did the 110 come from?
Oh, right. Okay, yeah. The 110, the denominator here is basically looking at the fact that you have 110 possible comparisons. So we have 10 data points in phase A, right? And for each of those, you're doing 11 comparisons of overlap. So 10 times 11 is 110.
Thank you so much.
Sure. Okay, so we can see that there are applications here for reversal designs, right? The AB type of design, or any kind of combination of reversals. But for multiple baseline, there are also applications that come in 3 different flavors, right? You can have multiple baselines across subjects, across stimulus conditions, and across behaviors. I don't know if you guys covered that earlier today. If I can get some nods or some shakes.
Yes.
Yes? Okay, good. So I don't have to go into that. But basically, you can examine the degree of similarity across subjects. So is there a consistent effect across subjects? That can certainly be one of the applications that, again, helps in understanding how effective a intervention is. So we're basically looking at generalizability and just overall robustness of an intervention. Also across stimulus conditions. So again, if you want to look at the degree of similarity of percent non-overlap across contexts, that can be good. But also you can check for whether the change in one condition generalizes to other contexts. Meaning, before you introduce the intervention to another context, you can already be since you're already tracking the behavior in the other context, you can look at whether or not there is a change in those other contexts before you introduce it. And if there is, then certainly that's useful information because it means that in introducing the intervention in one context, it's already generalizing to others, which means that it might be more powerful, or in fact, the flip side might be if you don't want that to happen, you also want to know that. Does that make sense? Nods or shakes?
Yes.
Yes.
All right. And then finally, it can generalize across behaviors. Similar to the previous point where if you have other behaviors that you will set up an intervention for later in time, you can already start looking at whether or not there's any change happening after you introduce the intervention for a specific behavior and see if it bleeds into the others. Well, it bleeds into, generalizes. Okay, so that's it for NAP. Now, we have literally a minute. So I'm just going to put this slide up here and show you, remember what I talked about where all of these kinds of quantifications don't take into account what happens once you're above 100% effectiveness, right? Once all the intervention data points exceed all of the baseline data points, it's all just 100% effective, right? So this is where these parametric tests come into play. And there are a couple of different measures. If you have an equal number of observations in both phases that you're comparing, you have a formula here for calculating the standardized mean difference. What the heck is a standardized mean difference? What it is, it's the number of standard deviations apart that the two phases are. Anybody familiar with standard deviations? Show of hands. Okay, a few people. Unfortunately, we don't have time to go into it, but what I will refer you to is this article here, Durlac 2009.
We do a couple more minutes. I think we go to 13.
We have, what did you say? How much time do we have?
15 minutes.
Oh, okay, cool. All right, so then I will bore you to tears with the math.
They appreciate it.
Yeah. So okay, here's what this means. Cohen's d. It's very, very common in large sample studies where you have 20 observations in one group, 20 observations in another group, 100 in this group, 100 in that group. These kinds of studies don't really apply to ABA because you've got one participant, right? And within that participant, you're lucky if you can get 5 baseline observations and 10 intervention observations, right? So if you have those kinds of small numbers, what happens is, and what I'm talking about now is why these are not necessarily super useful in single case research, but you can still use them if you have these kinds of rare cases where you do have 100% non-overlap. So Cohen's d applies if you have equal numbers of observations in the baseline and the intervention, or whatever 2 phases you're looking at. If you have equal numbers, then you would use Cohen's d. And so what you do is, in Cohen's d, you have 3 pieces of information. There's the m sub e, which is the mean of the experimental condition. This would be the intervention phase. And the mean of the control condition, which is what C stands for, which is the, anyone? Bueller? Baseline, I heard it. I heard baseline, yes. And what that means is, okay, so you take the average value for the intervention, subtract the average value for the baseline. And that gives you the sort of absolute difference. So in terms of our example here, I mean, I'm not going to calculate this. Actually, yes, we have 15 minutes, right? So let me grab my calculator here. And so basically we're saying, what, 4 plus 3 plus 4 plus 3 plus 4 plus 7 plus 5 plus 2 plus 3 plus 2. 37. If anybody wants to double check my math, please do. Divided by 10. So the average is 3.7, right, in the baseline. And we subtract that from the average in phase B. So we've got 5 plus 9 plus 7 plus 9 plus 7 plus 5 plus 9 plus 11 plus 11 plus 10 plus 9. 92, okay, not bad. Divided by 11, the average is 8.36 repeating. That's a pretty big increase over 3.7, I'd say. So it's an improvement of 4.7 about, right? Okay, that's interesting in and of itself, but what we actually need to include in this is the denominator. And the denominator is the sample standard deviation pool. What the heck is a sample SD pooled? Well, here is the answer, this lower equation here. What it's basically doing is it's taking this difference of 4.7 and standardizing. Remember I said that this is a standardized mean difference test? And when you standardize it, it means, okay, so you got 4.7 units of change. A standard deviation is a measure of it's the average deviation of a data point from the mean. So I'll let that sink in for a second. The average deviation of a data point from the group mean. So in the intervention, we have a mean of 4.7, right? But we have a bunch of values that deviate from that value of 4.7, right? So how much does 5 deviate from 4.7? You say 5 minus 4.7, 9 minus 4.7, 7 minus 4.7, blah, 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 blah. Oh, no, I'm sorry, no, the 4.7 was the difference. What was the average for the intervention again? It was like 8 point something or 9 point something? 8.3 something? Thank you. So yeah, so you say, okay, 5 minus 8.3, 9 minus 8.3. Some of them are below the mean, some of them are above the mean, right? What you do is you take the average of the deviation. Whether it's positive or negative, you make them all positive, and then you just compute the mean deviation. And that tells you, on average, how much does every data point in that group deviate from the mean of the group. That's a standard deviation. So it basically tells you, well, the equation in the end tells you if you have the difference between the groups divided by the standard deviation, it tells you, okay, on average, how many standard deviations apart are these two groups? If you've never dealt with standard deviations, it might be like a little bit tricky to wrap your head around. But essentially what it does is it puts it in terms that are universal across both groups. So one group is going to have one standard deviation, the other group is going to have a different standard deviation. Well, what you want to do is get like an average standard deviation for both groups, which is what this pooled SD does. You can see that it takes the SD of the experimental group and the SD of the control group. So again, the intervention group and the baseline group, and just divides by 2. So it just takes the, I mean, you know, you have to square it and then make the square root, but essentially what it does is it allows you to take an average standard deviation of both groups. And then you plug that back into here, and what you end up with is, you know, an absolute difference, which was what, 4.7, divided by the standard deviation. And what that then does is it tells you, okay, well, if you take a number and divide it by a standard deviation, that then tells you the number of standard deviation apart that the two groups are. To me, that makes sense. I deal with this stuff every day, so I'm sorry if it's a lot to take in, but we don't have to worry about all this. This is a correction factor. This is the real core of what's going on. So let me open it up to questions, because I'm not sure if this is going to make 100% sense to everyone. So if there are questions, just shoot. And if not, you can always email me. We can set up a time to talk. Again, this is just a little appendix here.
Nobody has anything else. So my question is, when we do our dissertation and we're at the point and we collected all our data, as a methodologist, you're going to assist us to select the right, because to me it makes sense to just build this in, especially if you're thinking of getting a grant, since now grants you really need this kind of quantification. Would you assist us in determining what we need at this point? Because we still need to understand how to write up this data. So
no, definitely. I wouldn't want you to just, you know, kind of do this in the dark or anything like that. I think that as far as NCAID services go, my services go, and NCAID, this is one of the things that I can definitely help you with. You're going to have, you know, it's a long journey that you're embarking upon. This presentation here is just sort of an introduction into this world, right? So when you're actually at the point of figuring out how to take your data and kind of quantify all this stuff, yeah, shoot me an email. We can set up a consultation to meet, and we can talk about all the different options, certainly.
And Peter, we'll have a lot more discussion linking these elements coming further.
Like a whole course.
That's great. That's right. This is the tip of the iceberg. So
all of this again. So, and how these pieces fit in the process.
Yes.
Yeah. Okay. So that being said, there's a whole other equation if you have unequal numbers of observations across phases. So that's called Hedges G. And so again, a lot of the time you might have, let's say, 5 observations in baseline, but 10 during the intervention phase. And there, Cohen's D is inappropriate. And you know, without going into the numbers, what Hedges G does is it gives more weight to the larger sample, so that a smaller number of data points don't unduly influence the estimate. That's all that is. The only difference between them is the way that you calculate the pooled standard deviation. So you can see, generally speaking, you see that everything is the same, right? You see SD of the intervention phase squared, just like it is up here, plus the standard deviation squared of the baseline phase, just as it is here. The difference is that you're multiplying each of them by the number of observations. That's what this N stands for. It's the number of observations in the intervention phase minus 1. And here it's the standard deviation of the baseline phase times the number of data points minus 1. So what that does is it basically says, okay, give me a correction factor for the number of data points in each of those standard deviations. And when you multiply the standard deviation by the number of data points, it kind of, if you have twice as many data points in one phase, that standard deviation that you're multiplying it by is twice as large. And then you break it back down by adding those data points into the denominator. So if you dust off your algebra book, this will all make more sense. But in the meantime, trust me that this is a very accurate way to basically prevent the smaller phase from unduly influencing the estimate of the effect size. Right, so just to recap though, again, these parametric measures only make sense if you have a very large effect in the intervention, i.e., greater than 100 or greater than 100% effectiveness. And then once you're above 100%, it could be, using the non-overlap techniques, it's all going to be the same no matter how much of an effect there is. But these two techniques allow you to quantify how big that increase over 100% is. That being said, I talked about small numbers of observations being really sensitive to outliers. So if you have an outlier in one of the samples, or I'm sorry, one of the phases, then it's going to affect the mean, right? If you have a bunch of 2s and 3s and then 1 10, and then you take the average of those, that 10 is really going to skew that estimate of the mean away from what is really going on with the 2s and 3s, right? So all of that means that you have to treat Cohen's D and Hedges G with a little bit of caution. And that's why, single case research designs use these kinds of non-overlap techniques, because these parametric tests are, not super appropriate, but again, they do act as a good corollary under the right conditions. So with that, what I want to do is I want to point you to the references that have a lot of background information on all these different techniques. I don't know if you want to write them down. What you can do is instead email me, and I can send you a copy of these slides, and that way you'll have access to all this stuff. There's my email down there. It's nk.me at the Chicago School. You've also got my phone number, which is my direct office line. So feel free to reach out that way too. And like I said, this presentation is going to be available on YouTube, which reminds me I should probably stop recording because that's not going to be